All right, 12.3, probability with counting, permutations, and combinations. So now we're going to take what we learned about counting, permutations, and combinations and actually apply it to probability. So objective, students will be able to calculate probabilities that involve permutations and combinations. So still, remember, probability is just favorable outcomes over total possible outcomes. But when we're calculating probability of different combinations, we have to do the combination, the way we count favorable outcomes is by doing the combination of all those favorable outcomes, or n choose r, and I'm doing n1 r1 because this is the first r, this is the number of successes, over the number of combinations of ways that we could get total possible outcomes or successes plus failures. So this is how we count those things when they're combinations. So let me give you an example. And this is where it gets real interesting. So you're playing the card game Hearts. In this game, 4 people are dealt 13 random cards. So you get 13 out of the 52 cards. What's the probability you receive all 4 aces? All right, so this is where it gets really interesting. In order to do this correctly, we first have to count. We have to think about the ways to get 4 aces, and I should say number of ways, and that's supposed to be an S, over the number of ways to just get 13 cards. That's essentially the 2 things that we need to count. And both of these are a little bit, no, they're not hard, but they're just to take a little bit of thinking about. So let's first address the ways we can get 4 aces, because I think that's the more challenging part here. So let's just imagine what that hand would look like, okay? I'm going to draw a bunch of lines here. So here's my cards. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 cards. I know, a lot of spaces, right? And we already know that if I got 4 aces, then 4 of these spots have to be aces. All right, so what's left then, right? So that means that I have 13 minus 4 is 9. There's 9 cards here left. And in order for me to get 4 aces, I have to already have the 4 aces in these first 4 spots. Now, I'm saying first 4. Order doesn't really matter, right? I got to have an ace here, ace here, ace here. It doesn't matter as long as I got 4 aces. So if I got the 4 aces, then really I'm just thinking about the combination of these 9 other cards. And so I really have spots for 9 other cards out of how many cards are left in the deck if I already have 4 aces. Well, there's 52 normally, but 52 minus these 4 is 48. So that means the number of ways to get 4 aces, or the number of ways of successes, is going to be 48, because that's how many cards I have to choose from. Choose the 9 other spots. Again, there's only one way to get the first 4 aces here, right? Because it's combination, not order. It's just combination. There's only one way to get the first 4 aces. So we really only have to worry about counting up all the other ways we could fill the other 9 cards. It's a little bit different to think about that way, but that's how we do it. Now, remember, we want to put that over the number of ways to get 13 cards. Well, the number of ways to get 13 cards out of all 52, right? Because we're talking about all possible outcomes. Well, that's just 52. Choose 13. Okay, now you could work these all out. 48 choose 9, 52 choose 13, but I would recommend putting this into your calculator. Your calculator has the ability to do this. Just, you need to make sure, use parentheses and divide, but you're looking for, it should either look like combination NR, or it'll look like, how I write it here, it'll look like NCR. That button is somewhere on your calculator, and all you got to do is press the 48 first, then this button, and then 9. Again, you want to put that in parentheses, and then divide by 52, this button, and then 13. If you're using a graphing calculator, it's underneath the math menu. You got to go to math and then probability and scroll down and find it. But it's in your calculator. If you're not able to do it now on your own, that's not a big deal. We'll work on that in class. But I'm going to go ahead and do it on my calculator. So 48, I find the choose button, 48 choose 9, divided by, and if I was to just put this in, it's going to be a huge number. So that's why I'm going to put them both in the same time, because it'll let it reduce. 48 choose 9, divided by, in parentheses, 52 choose 13. 13. 52 choose 13. All right, and it's going to give me a decimal. When I plug this into my calculator, it gives me a decimal, but my calculator actually can convert it to a fraction. So the decimal I got is approximately 0.0026 with some other things going on afterwards, but the fraction would be 11 out of 4165. Okay, so it would happen 11 out of 4,000 times, so pretty interesting. Not very frequently that you get 4 aces. And there is, of course, you don't have to do this in the calculator. It just gets to be a lot of work. You could use the combination formula we have, do that, put it over the combination formula with 5213, and things just start canceling out until you're left with 11 over 4165. It's just a lot of work for this little video. All right, so in the similar regard, I want you guys to try and do practice 2 on your own. I'm going to start you off though, because now you're playing. It's a very similar problem, but now you're playing a 7-card poker game, like Texas Hold'em. So now instead of 13 spots, you have 7. And we're asking a very similar questions. What's the chances of you getting 4 aces again? So again, your first 4 spots, the way you can think of it is your first 4 spots have to have aces in them. Again, order doesn't really matter here. We're just kind of using that language. So what about the other 3? What's the combination of all the other 3 cards could be? That's really all your ways of getting 4 aces. So I'm going to let you kind of think about that and then check back when you're ready to check your work. Okay, that's a pretty cool problem here. So remember, we have 3 other spots. So we got to think about how the 48 other cards can fit in these 3 spots. So that'd be 48 choose 3 over 52 choose 7. Now there's a couple of things about games like Texas Hold'em is that if you're playing a game like Texas Hold'em, there would have to actually be some other cards displayed. In fact, there should be, by the end of the hand, there would be at least 3 other cards displayed, meaning 3 other cards that are known. And so it gets a little bit more interesting in that if you got 4 aces known and another 3 cards are somewhere displayed on the table, well, that takes away from the cards that you could choose from, right? We said there's another 48 cards to choose from here because we already picked 4. But if there's 4 here and another 3 on the table, well, now there'd only be 45 cards to choose from. So just some things to think about how that could be calculated a little differently depending on the game you're playing. So if you are playing Texas Hold'em and you knew what those other 3 cards were, you'd have to change this. But we don't know what they are according to this problem, so we're just going to leave it right there. Okay, kind of interesting, right? All right, let's go on to permutations with repetitions. This is kind of interesting. The number of distinguishable permutations of n objects in which one object is repeated r1 times and another repeated r2 times and so on is this little equation. So this is really useful for problems like this where you're rearranging letters. So basically, you're going to put your number of items on the top, factorial, and then your number of unique items in each one of these. So, for example, I got this word Mississippi, and we're going to figure out how many ways you can arrange the letters of Mississippi. But since we have some letters that repeat, actually lots of letters that repeat, we're going to use this formula here to figure it out. So, first of all, how many letters do I have total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that means I put 11 factorial on the top. And now, what are all my different letters? I'm going to write them over here. We got an M. How many times do I have an M? It looks like just once. I have an I. It looks like I have an I 4 times. I have an S 4 times. And it looks like I have a P 2 times. So what we do is we really are just going to list all these numbers in here. But do I really need to list 1 factorial? I mean, 1 factorial is really just 1. So that shouldn't really matter. So you don't have to list the ones. But we do have to list the 4, 4, and 2. So we're just going to do 4 factorial, 4 factorial, 2, factorial. Okay, and we can actually we could simplify this out pretty easily because this is like saying 11 times 10 times 9 times 8 times 7 times 6 times 5 times, there it is, 4 factorial, over, let's just leave the 4 factorial. And then the other 4 factorial would be 4 times 3 times 2. Don't really need to put the times 1. And then 2 factorial is really just 2. So let's see what cancels out. Definitely this cancels out with that, which is nice. And if we just kind of look at this, what about 6? Well, 6 would cancel out with 3 times 2, and 8 would cancel out with 4 times 2. So now we're really just left with 11 times 10 times 9 times 7 times 5. And we could put that all in our calculator. When we do, we get 34,650. Boom. And so that's the number of ways you could arrange the word Mississippi. Pretty cool. Let's go to the next one. All right, it's up here at the top. Not a lot of space for it. I'm asking how many different ways can you arrange the word algebra. This one's quite a bit easier though, because there's only, the A is the only letter that repeats. So it should be pretty easy to do. Go ahead and give it a shot and then check back when you're ready. All right. Well, there was 7 letters, so I put 7 factorial. A was the only letter that repeated, so all the rest just showed up 1 time, so I didn't really need to list them here. But since A repeated twice, I put in 2 factorial. 2 factorial is really just 2, but it doesn't really matter. It cancels out with itself here, and you're left with 7 times 6 times 5 times 4 times 3, which is 2,520. So there's over 2,500 ways you could arrange the word algebra. All right. Now we get into some really fun stuff here. This is where it gets really interesting, and I'm going to show you how to use this formula here, and then in class I'll show you guys another way to do this. But since we can count repetitions with what we just learned, with that little formula we just learned, we can now start calculating, since this is the number of repetitions, we can start calculating probability when we have repetitions, because this would be our number of successes over our total number of possible outcomes. So what you do here is, just like we did here, that's the same formula as what we used on the last 2 problems. But now we're going to put that over b to the n, where b is the number of possible outcomes for one event. So if you're flipping a coin, there's 2 possible outcomes, so this would be 2, and n is the number of events that you have. So if you flipped it 3 times, this is 2 to the 3rd. So a couple things here real quick. When you're dividing by a number like this, you see you got a fraction here divided by a number. Well, you could kind of think of this as a number over 1, and you could flip and multiply. It's 1 over b to the n. So you can kind of simplify this to n factorial over p factorial, q factorial, and then b to the n. Now remember, this formula would change if you had more than one thing repeat. A lot of times we're only going to have 2, and so that's why I gave you this formula, but theoretically you could have 3 different outcomes, and then this would be like a 3 to the number of trials. So we're going to use that in this first problem here. Now, before I actually do it the algebra way, I'm going to show you a tree diagram. I guess there's actually 3 ways. I'm going to show you 2 on video and a whole other way in class that's pretty interesting. So let's just think about this. Let's just try and draw a map of what could happen here. Because they say find the probability of flipping a coin 3 times and getting heads exactly twice. Remember that getting heads exactly twice, if you're flipping it 3 times, is going to mean that you get tails once. That's kind of important, a way to think about this. So not only are you getting heads twice, if it's exactly twice, you're going to get tails once. All right, so let's go over here and think about all the ways that we could get heads twice. So think of this as 3 stages. You got your stage 1, you got your stage 2, and you got your stage 3, your 3 flips. On the first stage, it's either heads or tails. And then after that, if you got heads, then it's either heads or tails again. And if you got tails, then it's either heads or tails again. And then you could see where this is going, hopefully. Then this is either going to be heads or tails on the 3rd stage. Same thing here, heads or tails. Same thing here, heads or tails. And then finally, heads or tails. And so we have these 8 pathways here. You could see these kind of 8 ways to go down this tree. That's why this is called like a tree diagram, because it keeps branching off. Now obviously if we were doing something like 20 trials, it'd be way too difficult to draw this out. You would just need so much space and it would just get really convoluted. But this kind of shows you where the math comes from. So let's think about which one of these pathways had 2 heads in it. Well, this first pathway had 3. So that does not work. The second pathway had exactly 2, so that's a success. The next pathway, 1, then a tails, then a heads. Yeah, that's a success as well. The next one had 2 tails. That's not what I'm looking for. The next one had 2 heads, so that's a success. And then we see that we got only 1 head here, only 1 head here, and no heads here, so these are all failures. All right, so let's think about that. How many successes did I have? I had 3. How many total trials? Well, I had 8. So my probability of getting exactly 2 heads is 3 out of 8. Now, that was how we do it as a tree diagram. Again, as we get more and more trials, you're not going to be able to do a tree diagram, so we need some equations to use here. Well, that's what this guy's for. So let's identify all of our different variables here. The n is the number of trials, right? So the number of trials here is 3. So we're going to say that n equals 3. Where p, we'll say that's like the number of successes or the number of heads, and that's 2. Which would make q, like in this situation, p and q should always add up to this. So that would make q 1, which means it's not really all that relevant. And b, remember b is the number of possible outcomes. Well, we're flipping a coin, so there's just 2 possible outcomes here. All right, so let's plug it all in. N is 3, so I'm going to write 3 factorial over p is 2, 2 factorial. I don't even really need to put the 1 factorial here, right? 1 factorial is irrelevant, it's just 1, so I'm going to skip it. And b to the n, so b is 2. And n, again, which n shows up again, n is the number of trials here, so that's 2 to the 3rd. Well, 3 factorial is 3 times 2 times 1. We don't need to put the 1. 2 factorial is really just 2, and this is times 2 to the 3rd. You can see these two 2's cancel out, and you got 3 out of 8. Hey, look at that. Boom. So that's pretty easy. If you know that formula, that'll work. Again, I'm going to show you another way in class that's I think pretty amazing that it does work. And very useful for some really big probabilities, like really big events, like maybe like 10 events or something like that. Okay, so practice 3. Not that much different. Very, very similar type question. Now we're flipping a coin 5 times instead of 3 times, and I want exactly, I'm getting tails exactly 3 times. If I get tails 3 times, that means that I must get heads exactly twice, or 2 heads, right? Important to think about it that way, because that's how you define your P and your Q. All right, give it a shot, and then check back here when you're ready to check your work. All right, so your N is 5, because that's the number of times you're flipping the coin. Your P is 3. I'm saying 3 because 3 tails. You notice something, if you switch the P and the Q, it actually doesn't matter because it's the same thing. Q times P is the same thing as P times Q, even though it's factorial. So your 2 would be, or your Q would be 2 factorial, and B is the number of possible outcomes, so that's 2 because you're getting heads or tails. So I put 5 factorial over 3 factorial times 2 factorial times 2 to the 5th, and then I just kind of started expanding and canceling some stuff out here. So I got 5 times 4 times 3 factorial. Well, I already have a 3 factorial down here, so I just stopped there and canceled it. And down here I had 2, because 2 factorial is just 2 times 2 to the 5th. Well, I thought of 4. 4 is really like 2 squared, so if I canceled out 2 squared with a 2 squared into the 5th, I'd be left with 2 to the 3rd. So on top I just have a 5, and then I have 2 times 2 to the 3rd, which is 16. So 5 out of 16. Just some playing around with some exponents there, but nothing too difficult. All right, I want you guys to go ahead and give this summary a try. I will see you guys on the next video. Don't forget to write at least one question from the notes too, and I look forward to showing you the binomial theorem, which will kind of help us do problems like this as well in class. Bye.